In this lecture, we're going to talk about forces, the moment of a force, and then force and moment systems. Now, you can't really do much at all, really, in engineering until you understand what these quantities are and how do we manipulate them. So let's start off with a fairly straightforward one here. What is a force? Well, a force is simply the product of a mass and an acceleration. And so we could say that a mass of 1 kilogram here on Earth experiences an acceleration due to gravity of 9.81 meters per second squared. And so it exerts a force of 9.81 newtons. So it's the product of those two numbers, the mass and the acceleration, that gives us the magnitude of force. Now, put another way, we could say that a mass of 1 kilogram experiences an acceleration of 9.81 meters per second squared, and therefore it exerts a force of 9.81 newtons on whatever it's sitting on, for example. So that then brings us nicely on to newtons. So newtons are the unit of force. So we'll start off, we'll write the fundamental relationship here. Force is equal to mass times acceleration. And if we throw some numbers on that, we can say a mass of 1 kg, it would experience an acceleration, so just think about a rock sitting on a table or something, right? Experiences an acceleration due to gravity of 9.81 meters per second squared. And that yields a force of 9.81. And if we do the units, if we use the kgs and meters per second squared units, well then we just end up with kgs times meters all over seconds squared. That was the same as 9.81 newtons. And from that then we can infer that 1 newton is 1 kg meter per second squared. Okay, so let's just take another example then. If you take your weight, let's say the average weight of an average person is, let's imagine 80 kgs. Now I don't know if it's 80 kgs, bit more, bit less, but take a person. They have a mass of 80 kilograms or 80 kgs, but they exert a force of 80 by 9.81 meters per second squared, which is about 785 newtons. Okay, so what I'm trying to really drive home here is the difference between mass and force. Mass has units of kilograms, but force has units of newtons. So the force is what we get when we multiply the mass times an acceleration. So the very first trip up that you might make, that you want to get really clear in your head, the first mistake you want to avoid is confusing mass and force. Okay, mass has units of kilograms, and force is what we get when we multiply that mass by some acceleration. Okay, and that has units of newtons. So let's just write that other example. So we said you have a mass of, let's say, 80 kgs, plus or minus, but key difference, you exert a force of 80 kgs times 9.81 meters per second squared, right? So if you're standing on the ground, you exert a force of 80 kgs times 9.81, presuming you're here on Earth, meters per second squared, which is about 785 newtons. All right, and an alternative unit for that is in kilonewtons. So if we divide it by 1,000, we'd get 0.785 kilonewtons. Okay, so what we've discussed so far is the magnitude of a force. Okay, but that's not the full story. In fact, that's only half the picture. To fully describe a force or define a force, we have to define two quantities, right? We have to define a magnitude, which we've talked about already, but we also have to then define a direction, because a force is a vector. And as you know, vectors have magnitude and direction, as opposed to scalars, which only have magnitude. Okay, so now we're going to expand our thinking a little bit here, and we're going to start thinking about forces as vector quantities. Right, so the first key thing we're going to say here is that forces have magnitude and direction. And as a result, we recognize them as vectors. And I'll put in brackets here, not scalars. All right, so let's take a simple example here. Let's imagine a force, a two-dimensional force in an XY plane. All right, so here we have some force F, and it's sitting in an XY plane. Now, just for completeness, I'll say that, or I'll state the origin of the force. So the origin of the force, i.e. it's applied at location 2, 2, right? So 2 in the X and 2 in the Y. Now, the force has a magnitude, which we're indicating here as F, which is simply the length of the vector. So if I wanted to define this force here, right, I'd want to, first of all, say, what's its magnitude? So in other words, what's its length? So let's imagine, let's go for green here. Let's imagine it has a magnitude, the force F has a magnitude of 100 newtons, right? So that's going to get represented as the length of the vector. All right, but again, that's only half the story. we have to also indicate the direction of the vector. So we can do that simply by stating the angle that that vector makes with one of our axes, and we're choosing the x-axis here, the positive x-axis. So in other words, if I was to say, let's go for a different color, let's imagine this is our positive x-axis, so it's an arrow pointing in the positive x direction, therefore the positive x-axis, and then we're defining 30 degrees here as the angle that that force F makes with the positive x-axis. Okay, and that's how we fully define that force. And if we wanted to be really pedantic about it, we'd have to say that it makes an angle of 30 degrees in the counterclockwise direction, right, as opposed to 30 degrees clockwise from that positive x-axis. Right, so let's just get a note on that then. So to describe F, we need the magnitude, which is 100 newtons, and we need direction. And so I'm going to define the direction here as 30 degrees counterclockwise from the positive x-axis. Okay, so the next thing that we're going to start thinking about to just expand this idea of forces as vectors is the idea of the components of a force vector, right? So any vector on a 2D plane can be represented by two orthogonal vectors, two orthogonal components. Now this happens to come in really handy. This is really, really useful because this allows us, as we'll see now shortly, this allows us to combine the influence or work out or determine the combined influence of multiple forces in a really easy way. So let's just catch ourselves up with some notes here. So we're going to talk about components. We'll say components of force vectors, and we'll say that the first headline here is that any vector on a 2D plane can be represented by two other orthogonal vectors. And if it was a 3D vector in a 3D plane, it could be represented by three orthogonal vectors, but we'll confine ourselves to the 2D world here for the time being. Now, the other term here is orthogonal vectors, right? That's just a fancy way of saying two vectors that are at right angles to each other. They're mutually perpendicular vectors. Right, so let's take our force from up here and consider it as two separate vectors, two components. What we want to do now is break that vector up into two orthogonal components, and usually the most convenient way of doing this is to break it up into two components that align with your axis system. So in our case here, we have an X and a Y axis. And so what I really want to do is work out what are the X and Y vector components of that force vector, right? So if I come along here and go for red, well, we can see the components visually. The horizontal or X component is going to be this guy here. It's just the vector projected down onto the X axis, right? And so that's going to be Fx, and then the vertical component, the component in the y direction or along the y-axis, is just our vector projected onto the y-axis, Fy. Okay, and so the two components of this vector, along with the vector itself, make up a right angle triangle, where the original vector is the hypotenuse, and then we've got Fx and Fy being the two sides. And then it's just the basic geometry of a right angle triangle to determine the magnitude of Fx and Fy. And so we can rattle through that fairly quickly. So we can say Fx is going to be equal to F times the cosine of the angle. Okay, and plugging in the numbers, we've 86.8 newtons. Great. And then similarly, we can say Fy is just going to be F times the sine of the angle, which works out to be 50 newtons. Okay, so this is just your standard right angle triangle. And of course, we can confirm that we get back to the original vector by using Pythagoras. So we can say that the original vector, if I only had the two components, the original vector would be the square root of the sum of the two sides squared, right? So 86.6 squared plus 50 squared. Square root of all that should get me back to my original vector, which of course it does. And so, as I said, usually we're going to resolve our vectors into x and y components that are aligned along my x and y axis. But any orthogonal vector pair will work. So if we imagine the exact same vector with a rotated xy axis system, we could determine the orthogonal components aligned with that rotated axis system just as easily. So let's imagine the exact same vector, but imagine now we have rotated our reference frame. And so now we have an x prime, let's call it, and a y prime. Okay, so we can now determine orthogonal components with reference to this rotated frame just as easily. So our x prime component would be something like this, parallel to the x prime axis, and our y prime component would be something like that. And of course, we'd need to specify what is the angle that our vector makes with respect to the new rotated x-axis. And so let's imagine that it was 70 degrees. So that would be that angle there. And of course, we could work out our fx prime and fy prime in exactly the same way. And so I won't go through the numbers, but basically you can very easily work out that fx prime is going to be 100 times the cosine of 70, which would be 34.2 newtons, and fy prime would be 100 times the sine of 70, which should be 94 newtons. Okay, so where this ability to break vectors up into orthogonal components actually becomes useful to us is when we are combining the influence of multiple force vectors. So by breaking up these force vectors into their components, it allows us to easily determine the influence of multiple forces. So let's see this in action then. So let's imagine an xy plane and then two force vectors in that plane. And our objective is to determine the combined influence of both of those forces. Okay, so we've got two forces in an xy plane. We've got force 1, F1 is located at position 2, 2, it's orientated at 30 degrees. So that's the same guy that we were looking at previously. Now the second force is located at 10 along the x-axis and 8 in the y, and it's orientated at 40 degrees measured clockwise from the negative x-axis, and it has a magnitude of 60 newtons. And our task is to determine the combined influence of both of those forces. So what's the combined force effect of both of these forces? Well, the easiest way to do that is to break each of these two forces up into their two orthogonal components and then just add up all the components in the x direction and then add up all the components in the y direction. So let's start off here and just draw on the force components. Let's call that fx1 and then fy1, and then we'll do the same for f2. Well, we've already worked out the components of f1, so we can straight away, from what we've done already, we can say fx1 is equal to 86.6 newtons and fy1 is equal to 50 newtons. We can say that the x component of force 2 is going to be the magnitude 60 times the cosine of 40, which works out to be 46 newtons, and fy2 works out to be 60 times the sine of 40, which is 38.6 newtons. Okay, so now what we got to do is work out the total or combined horizontal force, and we can do that just by adding up the two x components. So we'll say the total or combined horizontal force. So we'll take the sum of the forces in the x direction, and we're going to assume that forces that act to the right are positive. So we're basically at this point stating our sign convention, right? So our sign convention is assuming that horizontal forces to the right are positive. And based on that, we can say, well, what have we got? We've got the fx1 acts to the right, so it's going to be positive. So that's 86.6. The 46 for fx2 acts to the left, and so it's negative. So that's minus 46. That gives me a resultant force in the x direction of 40.6. So we could say that Fx total is equal to 40.6 newtons. Now notice that this is a positive number, and according to our sign convention here, that means that that acts to the right. And we can do the very same thing for the force in the vertical direction. And again, we're going to have to state a sign convention, right? So I'm going to assume that forces, so we'll just say that some of the forces in the y direction is what we're evaluating, but we're saying that forces acting upwards are positive. And so both forces act upwards, so they're both positive numbers. So it's 50 plus 38.6 should give me 88.6 newtons. All right then. So we're not done, right? We've got now what we've done is we've got the components of the resultant force. What we need to do is determine what's the magnitude of the resultant force. Okay, because we have its horizontal and vertical component. So what we've done is work out the horizontal component. What did I say that was? 40.6. We said the vertical component was 88.6. And what we now need are two things. Remember, to define a force, we need its magnitude and its orientation, right? So we're going to need, the magnitude is just going to be the hypotenuse of that right angle triangle. And we're going to define the angle here, alpha, as the orientation. And of course, basic right angle triangle stuff here, we're able to work out the magnitude FR and alpha pretty easily. So we'll say our resultant force FR is equal to the square root of 40.6 squared plus 88.6 squared, and that works out to be 97.4, I think. And alpha, the angle alpha, is going to be the tan inverse of 88.6 over 40.6 which should give me 65.4 degrees. So now, with that bit of information and that bit of information, we've worked out the equivalent force effect of both of these two guys, right? Both of these two forces, F1 and F2. So we're saying that F(or) has the same force influence as F1 and F2, but that's not the full story, because we haven't considered the twisting or moment effect of the force yet, right? So notice how we've defined F(or) here, but we haven't said where it is, right? It's just sort of floating in space there. We haven't pinned down and said, where would you have to apply F(or) in that 2D plane? And so we've got to take into account the twisting effect or the moment effect of F1 and F2. And when we do that, that's going to tell us where we'd need to place F(or) in order to have the same force effect, or what additional moment would we have to apply in addition to F(or) for the two systems to be equivalent to each other, for F1 and F2 to be equivalent to F(or) and some additional moment effect. So we're going to get to that, but let's first of all, we're kind of jumping ahead a little bit here. Let's first of all have a think about what is the moment of a force. So we've talked about forces, we've talked about the fact that they're vectors and therefore are defined by a magnitude and a direction. Now, before we, in fact, let me finish off the sentence here, we'll say we haven't considered the twisting or moment effect yet. Okay, so in order to do that, we have to first of all talk about what is the moment of a force. Okay, so if I take a force, some force, and I multiply that by some distance from some point, I'm going to get a moment, right? So we'll say the force, which is going to be in newtons, gets multiplied by a distance, which we'll assume is in meters, and that's going to give me a quantity called a moment, or a moment of the force, which is in Newton meters. Okay, so that's the first thing to say. The units of moment are force times distance, right? So in this case, it will be Newton meters, could be Newton millimeters, kilonewton meters, whatever. It's going to be a force times a distance. So let's consider a simple lever to expand on this a little bit. So we can imagine some rigid bar here. We can also imagine it balancing on some pivot point, also known as a fulcrum. Okay, so we kind of intuitively know that if I apply some force down here, F well, we kind of know from our kind of playground days that the force we'd have to apply for this thing to balance, the force we'd have to apply up on the right hand side here, FB, is going to have to be significantly larger than FA, because FA is a further distance away, right? So the moment, in other words, the moment that FA generates about that pivot point, about that fulcrum, is given by the magnitude of FA times the distance, and we're just going to call the distance delta A. So we'll say that's going to be delta A, and we'll say this distance here is going to be delta B. Now, if that thing is to be balanced, well then FA times its lever arm, the distance that it makes from the pivot point, has got to be equal to FB times its distance, delta B. Okay, and so this quantity here, we now know, is the moment generated by FA, and this is the same thing over on the right hand side, the moment of FB about the pivot. Okay, so the main point here is if I apply a force at some distance from a pivot point, it's going to generate a moment or a twisting effect about that pivot. Now the key thing here is that the distance must be measured perpendicular to the line of action of the force, right? That's an important one, right? The line of action of the force is the line, I'm drawing it on here, dashed red, right? That's of force A. The line of action of force A is that red dashed line, and that is the straight line along which that force acts. Now you'll notice that the distance, delta A, was measured at right angles to the line of action, okay? And the same thing over here. So there's the line of action of FB, and the distance delta B was measured perpendicular to that line of action. That is a crucial point. So we'll just put it on here. MB, distance must be measured perpendicular to the line of action of the force. All right, so now let's consider a force lying in a 2D plane. So let's take this idea of moments and sort of map it onto what we were talking about earlier, this idea of forces on planes. So if I set up a simple XY plane again, so we've got a force in our plane here, and remember we've got to give it a magnitude and a direction. So we'll say it has a magnitude of 50 newtons and it has a direction which is 20 degrees measured counterclockwise from the positive x-axis. Okay, and again, just for completeness, we'll just give it some coordinates where the force is applied. It's applied at coordinates 3 and 6. So the question is, what moment does that force generate about the origin. So you have to say, if you're going to specify or calculate the moment of a force, you got to say the moment about a particular point. You got to specify an origin point. And so what we're interested in is the moment that is being generated by that force about the origin here. Okay. First of all, let's map on the line of action of the force. Well, the line of action, remember, is that straight line along which the force acts. So it's going to be something like this. And so the moment that force generates, remember, it's the magnitude of the force times the perpendicular distance from the line of action, right? And so if we get the perpendicular distance between the origin and the line of action, it's going to be something out here. So just sort of eyeballing it on there, right? So there's your perpendicular distance. Let's draw on an arrowhead there and an arrowhead there, and let's call that lambda. Okay, so if I wanted the moment that force generates about the origin, it would be the force magnitude, in this case 50, times the distance lambda. Okay, so really you'd say to yourself, okay, well, how do I work out the magnitude of that moment? Well, I'd have to work out lambda. Now, that's one way of doing it. You could do that. But a much more straightforward way and a faster way is to, first of all, because lambda is kind of an awkward distance to try and work out, right? You have to put your geometry hat on and start thinking about how do you work that out. A much easier way is to just say, okay, well, instead of working out the moment that 50 newtons here generates, let's take the orthogonal components of it. Don't deal with the 50. Deal with its equivalent components, right? So you've got the x component and the y component, because I can work out the moment that the x component generates and I can add it to the moment that the y component generates, and I can work out the moment that those two components generate really easily because they're perpendicular or parallel to the x and y axes, right? So instead of working out lambda, what we could do is we could say, let's say calculate m, and instead of working out lambda, calculate the moment generated by the components of f. All right, first thing to do is work out the components. So again, relying on what we've seen already, the x component is going to be 50 times the cosine of 20, which is 47 newtons, and fy is going to be 50 times the sine of 20, which is 17.1 newtons. Okay, we can deal with that. To calculate the moment then, we're going to take the sum of the moments. Let's come over here to the left here, right? So we're going to take the sum of the moments about the origin, and we've got to state a sign convention again, right? Because a moment can either be a clockwise, because it's a rotation now, right? So it can either be a rotation in the clockwise direction or a rotation in the counterclockwise direction. And so I typically assume that clockwise moments are positive, right? So that's going to be my sign convention for moments. Okay, so instead of drawing the component vector in the y direction, instead of drawing it all the way out there, let's draw it here. Right, so let's call that fx, we'll call that fy. So to work out the moment, we're going to work at the moment that the fx component generates. So what's that going to be? Well, it's going to be the force magnitude, fx, which is 47, multiplied by its lever arm. Well, what's the lever arm of the component? Take your line of action back, and then the perpendicular distance is now just going to be that vertical distance, which happens to be the y coordinate, right? And the y coordinate we know is 6, right? So your lever arm for the x component is 6, the y coordinate. Now, that's a magnitude, right? Now you ask yourself, is the magnitude positive or negative? The way to work that out is you have to ask yourself, does this force here about this origin point down here, does that generate a clockwise or a counterclockwise moment? Well, that force would tend to cause clockwise rotation, right, about that origin point. Now, the way you can think about that is, or the way I often tell students to think about that is, when you're trying to work out whether a force causes a clockwise or counterclockwise moment about a point, what you do is imagine, you'll eventually get to a point where you can see it straight away, but before you get there, imagine you literally have this on a piece of paper, you stick a pin in the piece of paper at that location there, right? And then you literally push your finger along where the force is. So literally push your finger here and push in that direction, and ask yourself, what way does that piece of paper want to move? That piece of paper wants to rotate clockwise like that, okay? And so that moment, that tells us that force generates a clockwise moment because it wants to rotate the piece of paper that it's drawn on in the clockwise direction. Now, similarly, you ask yourself, well, what moment, clockwise or counterclockwise, what direction is the moment generated by Fy here? Okay, same trick. Imagine you've got a pin in the piece of paper at the origin. You put your finger here and you push vertically, right? And what does the piece of paper want to do? It wants to start rotating counterclockwise about your pin, about that origin point. And so the moment generated by Fy about that origin point is negative. So we said the moment generated by Fx, we said that was positive, and the moment generated by Fy was going to be negative. So first of all, what was the magnitude of Fy? Well, Fy had a magnitude of 17.1, and its lever arm was going to be the x coordinate, right? So that was going to be 3. So that's going to be 3. Okay, and then this whole quantity altogether, okay, so that's the moment generated by Fy. That whole quantity generates a counterclockwise moment, which is negative, right? So that's the sequence of steps, right? You've got your force, magnitude, okay, it's a positive number. The magnitude is always a positive number, whether it's pointing to the right, left, up, or down, right? So the magnitude is just a positive number. Distance, again, it's all a positive number. All these numbers in your moment equation are going to be positive starting off. And then once you've got the moment magnitude calculated, right, then you ask yourself, does that force, is that generating a clockwise rotation or a counterclockwise rotation? In which case it will either be a positive you put on or a negative. So again, we did the same for y, right? We said, well, we have a 17.1, positive number, it's a magnitude, times a distance, again, positive number, right? And that gave us a quantity here, a magnitude of a moment. And then we asked the question, is that moment clockwise or counterclockwise? And in that case, it was counterclockwise. So we stuck in a negative number there. And then you evaluate that expression and you get the value of the moment. Now, when you evaluate that, you're going to get 230.7 Newton meters, right? So I'm just going to say here that was clockwise, that was counterclockwise. Then you ask yourself, what's that? Is that clockwise or counterclockwise? Well, it's a positive number. And according to our sign convention, according to the sign convention that was used to construct that number, a positive number indicates a clockwise rotation. So that straight away tells me, the fact that that is a positive number tells me that the resultant moment is clockwise. So the resultant moment is clockwise based on our sign convention. Obviously enough, if that had come out to be a negative number, a negative 230.7, well then we'd know that the resultant moment was counterclockwise. And so just to really drive home the point here, we're just going to say that F, right, that force F generates a moment of 230.7 Newton meters clockwise about the origin. So the next related idea to introduce is the idea of force couples. Now, two forces form what's called a couple and generate a moment if they satisfy several conditions. So let's set ourselves up here and we can say that two forces form what's called a couple and generate a moment if. Okay, so what are these conditions? Well, the two forces have to have equal magnitude. They have parallel lines of action. So in other words, the two forces are parallel and they must also have opposite directions. They have to be acting in opposite directions. So if I have two forces and they satisfy these conditions, they form a couple and they generate a moment. And so we can visualize a force couple pretty easily. So we can imagine some force here like so, and let's call that guy FA. Now, if that's FA and we know it's one part of a couple, well, straight away we know what FB looks like, right? So FB is going to be parallel. It's going to have the same magnitude and it's going to point in the other direction. Now, one key parameter that I haven't identified or I haven't mentioned yet is the distance between them. The distance between them is our lever arm. Okay, so the distance between them very often indicated with the letter Z, and again, those must be perpendicular distances. And so we would say here that the moment, right, let's say M subscript couple, M couple is going to be equal to, so the magnitude of the moment generated is FA times Z, which is the same as FB times Z. Okay, now the other thing to say is that in this case, the couple I've drawn, ask yourself, what sense of rotation does M couple have? What sense of rotation is it? Well, it's a positive clockwise rotation. Imagine I stick a pin halfway between the two. What sense of rotation is generated by that couple? And it should be relatively obvious that it generates a clockwise rotation. If the directions of both forces were reversed, it would generate a counterclockwise rotation. So couples, as I've introduced them here, they sort of drop out of nowhere and kind of don't really seem like they fit in anywhere. They're kind of somewhat out of context, but I'm introducing them here because you are going to see as you progress through your study of mechanics and engineering, you're going to see this appear quite a lot, this concept of a force couple. And so we won't say any more about it now, but rest assured it's going to be something that you're going to bump into again and again. But again, it's not a very complex idea. Very, very straightforward. Two forces, they form a couple and therefore generate a moment if they have equal magnitude, they point in opposite directions, and have parallel lines of action. And the magnitude of the couple generated by those forces is going to be given by the magnitude of one of the forces times the lever arm, or the perpendicular distance between the lines of action. Okay, so next we can move on to the idea of equivalent systems. Now, everything that we've talked about so far in this lecture has all been leading up to this idea of equivalent systems. We've basically been filling our toolbox with all of the bits and pieces we need, all the tools we need to evaluate force and moment systems. Okay, so the systems that we're talking about are systems of forces and moments. Okay, so let's imagine we have two separate systems of forces and moments. Now, we'd say that the two systems are equivalent to each other if they satisfy two conditions. The sum of the forces in each system is the same, and the sum of the moments in each system are the same. And we can break that first condition down into the sum of the forces in the x direction must be the same, and the sum of the forces in the y direction must be the same, or the sum of the forces in any two orthogonal directions between both systems must be the same. Right, so I'm making this sound an awful lot more complicated than it is. So you'll see, it's actually not that complicated at all. So we're going to say here that two systems of 2D forces and moments are equivalent if ... Okay, condition 1. The sum of the forces, let's imagine the sum of the forces in the x direction within system A must be the same as the sum of the forces in the x direction in system B. Now, we'll also say that the sum of the forces in the orthogonal to x, so the y direction, in system A must be the same as the sum of the forces in the y direction in system B, right? So that takes care of the force equivalence, and then the moment equivalence must also be satisfied. So we'll say the sum of the moments in system A must equal the sum of the moments in system B. And we'll just say here that that's any two orthogonal directions for the force conditions. Like most things, this is going to seem an awful lot more straightforward when you see a couple of worked examples. So again, this is kind of fairly abstract. You're looking at this and sort of probably thinking, well, okay, it sort of sounds like it makes sense, but like, what's the practical value? So being able to evaluate the equivalence of different force and moment systems becomes very, very helpful when we have a collection of forces and moments applied to, let's imagine, a structure, for example, and we want to work out what would be an equivalent single force and moment that has the exact same effect. So that has lots of practical value to us as engineers if we want to work out the combined influence of many actions, many forces, many loads on a structure. Okay, so let's actually see some examples of this. And so to kick it off, we're going to return to our previous example. So previously, we had this force system on the left here, right? So we had an x and a y axis, and we had an origin. Let's call that the origin for system A, and we're going to call this guy obviously system A. Now, we'd worked out the resultant force in the x direction and the resultant force in the y direction. And we also worked out the angle of orientation and the magnitude of the resultant of those two resultants, right? And so let me draw that over here on the right hand side. Right, so we said that we had a resultant x component of 40.6 newtons, a resultant y of 88.6, and the resultant of those two orthogonal components was 97.4 newtons, and the vector, or the resultant, would be orientated at 65.4 degrees counterclockwise from the positive x-axis. So to make those two systems, system A on the left and we'll call it system B on the right, to make those two equivalent, we need to capture the moment effect of system A and apply it to system B. And so the question we have to ask ourselves is, what is the moment that is generated by the forces in system A? And we'll call that M subscript A. Okay, well, we know how to do that now at this stage, because what we can do is take the sum of the moments about the origin of system A We'll assume again that clockwise moments are positive, and once we work out that moment, we can apply that moment at the origin of system B, and at that point we'll have two equivalent systems. So again, try and do this yourself first. Work out the moment generated in system A, so the resultant moment of all the forces applied in system A, and that's pretty easy to do. So we'll take the horizontal component of the 100 Newton force first, so that's going to be 86.6 newtons, right? What's its lever arm? Well, its lever arm is going to be 2, right? So you take the line of action of that 80, come across here, and then the perpendicular distance between the line of action and the origin is going to be the y coordinate, which is 2, right? So we'll stick a 2 in there. Now ask ourselves, okay, well, what sense of rotation does that moment generate, clockwise or counterclockwise? Well, about the origin point here, that 86.6 would tend to cause clockwise rotation. Okay, or clockwise rotation. Imagine clockwise rotation of my whole axis system. My whole frame would want to rotate clockwise under the influence of that force of 86.6 newtons if my pivot point was the origin here. And so that means, according to our sign convention, that's a plus or a positive moment. Now, let's look at the y component. Well, that's 50 newtons and its lever arm is also 2 meters. So we'll say 50 newtons times a lever arm of 2 meters. And what sense of rotation would it cause? Well, about the origin, that force there would want to cause would try and cause counterclockwise rotation. And so that's going to be a negative moment. All right, and in that way we can continue building, right? So we can say our 46, so this guy here is going to have a lever arm of 8 meters, so the y coordinate again, okay, and it's going to cause counterclockwise rotation. So that's going to be a negative 46 by 8, and then the final one is my 38.6, my vertical component, 38.6 by a lever arm of 10, and it's going to want to cause counterclockwise rotation too. So that's this guy here. Right, and so we evaluate that expression and we get the total moment is a negative 680.8 Newton meters. Okay, what does that negative mean? Again, according to our sign convention, which says that clockwise moments are positive, a negative would indicate a counterclockwise, right? So the negative means a counterclockwise moment according to our sign convention. All right, and what does that mean? All of that means is we would apply MB equal to a negative 680.6 or 0.8 Newton meters on system B. Okay, and so applying that negative moment, let's go with orange here. There's the moment. Now, so that moment is having the same effect, 680.6, as it's having the same effect as the moment generated by this guy and this guy in system A. So system B now consists of the moment 680.6 and the force 97.4 applied at the origin. Now 97.4, that force of 97.4, it's not generating a moment. It can't generate a moment about the origin because it passes through the origin, and so it doesn't have a lever arm. Its lever arm is 0 about the origin. Okay, so now system A is equivalent to system B because each of our conditions has been satisfied. Right, so let's try and reinforce this idea of equivalent systems by working through another worked example. So here we are with another system of forces and moments, and we're asked to replace this system with an equivalent system consisting of a single force and moment. So pretty much the same thing that we were doing in the last example, but we just have more forces and moments to deal with here. So we have a force A. We can see it there, 100 newtons, a force B of 90, C of 40, D of 50, and then we haven't seen this yet, but we've got a moment applied at position 8, and that moment has a magnitude of 150 Newton meters. Okay, so we need to work out the resultant force in the X direction of all of these forces, the resultant force in the Y direction. We're going to use those two components to get the resultant force, and then we're going to get the resultant moment of all of these actions, these forces and moments. Okay, so the first task here is to break these forces up into their orthogonal components in the X and Y direction so that we can add up all the X's and add up all the Y's. So I'm going to just sketch on the ones that we need to resolve. So we're going to want this guy here, and it's a vertical component also. A and B are already horizontal and vertical respectively. So the only other one we need to resolve is going to be this guy and this guy. And I should also state that that is 45 degrees. Right, so let's go and resolve the forces into their orthogonal components first of all. So let's deal with force C first. All right, so the x or horizontal component will simply be 40 times the cosine of 45. So that's going to be 28.3 newtons. And the vertical component will be 40 times the sine of 45, which again is obviously 28.3 as well. So let's go ahead and represent those directly onto our main diagram here. And we need to deal with that 50 newtons next. Right, so the horizontal is going to be 50 times the cosine of 35 degrees, which should be 41 newtons. And the vertical component can be 50 or will be 50 times the sine of 35, which is 28.7. So let's just get those on the main diagram as well. All right, now it's just a matter of evaluating the sum of the forces and the sum of the moments. So I'll start off with the sum of the moments. So I'll evaluate the sum of the moments about the origin point down here. Now, again, make sure that you tackle this yourself first before you watch me working my way through it. So I'm just going to say, evaluate the sum of the moments about the origin. Right, so we're taking the sum of the moments about the origin and we're assuming clockwise are positive. All right, so the sum of the moments about the origin is going to equal. Now, let's just work our way through this bit by bit. So force A has 100 newtons. Okay, that's easy. That's 100 newtons pointing in the x direction, and it's going to have a lever arm of 2 meters. So let's have 100 times 2. It would generate a clockwise moment, and so it's positive. Then B is, B is 90 newtons acting vertically, right? So it's going to have a lever arm of 9 meters, and it's going to generate a counterclockwise rotation about that origin point. So it would be a negative 90 times 9. All right, now let's look at C. So C has 2 parts, right? So we've got the 28.3, well, it's 2 parts, they're both the same magnitude. And so it's going to be 28.3. The horizontal component will generate a clockwise moment and the vertical component will also generate a clockwise moment. One has a lever arm of 5 meters and one has a lever arm of 6 meters. So we can add that next. So that's going to be 28.3 by a lever arm of 5 meters. So that's the vertical component, plus 28.3 times a lever arm of 6 meters. So that's going to be the horizontal component. Okay, now we've got D, force D to deal with. So that was this guy up here. Right, so the horizontal component will generate a clockwise moment. So that's going to be 41 times 6. And then the vertical component is going to generate a counterclockwise moment with a lever arm of 1 meter. Right, so we'll say plus 41 by 6 minus 28.7 by 1. All right then. And then the very last thing we have to take into account, and we haven't seen this yet, this is new, but we've got this moment here. Now, a moment just gets added directly to the moment equation. It doesn't get multiplied by any distances because it's already a moment, right? We have to multiply our forces by lever arms to turn them into moments or to get the moment effect. A moment's already a moment, so it doesn't get multiplied by any distance. We simply add it into the moment equation, and if it's a positive moment, in other words, if it's a clockwise moment, it gets added as a positive number. If it's a counterclockwise moment, it gets added as a negative number, regardless of where it is in our plane. So that's a positive or clockwise moment in our plane, and it's going to get added as a plus 150 to our moment equation. So plus 150. And so when we evaluate that, we get 68.6, and again our positive number here is telling us that that is going to be a clockwise moment. So that's the sum of the moments about the origin. Okay, the next thing to do is to evaluate the sum of the forces in the x direction. So again, just state what we're doing. We're evaluating the sum of the forces in the x direction, and we're assuming forces to the right are positive. All right then, so just working through these one by one, right? So A was 100 newtons to the right. Let's just have a quick look here. So A was 100, force B has no horizontal component, so it won't feature. Force C has 28.3, again acting to the right, so positive. And force D is 41 acting to the right, so again, positive. So we just add up all of those guys. So we'll have the sum of the forces in the x direction is equal to 100 for force A, plus 28.3 for force B plus 41 for force D. That's 169.3 newtons. And we can, again, positive number, so it's acting to the right according to our sign convention. And then let's evaluate the sum of the vertical forces. All right then, so looking again at our main diagram, what have we got? Well, A is horizontal, has no vertical component. B is going to be 90 acting upwards, so it's positive. C is 28.3 acting down, so that appears as a negative number. And then D is 28.7 acting up, so it's a positive number. Note that, obviously enough, our moment is not going to feature in either of our two force equations. So we'll say the sum of the forces in the y direction, assuming upwards forces as positive numbers. So we can say the sum of the forces in the y direction is equal to our 90 minus 28.3 plus 28.7 should be 90.4 newtons. And again, positive number, which means it points upwards. All right, so we're nearly there. All we got to do is combine these two force components together to get the resultant, the single resultant force vector. Because remember, our whole objective here is to swap out, is to take this system and swap it out or replace it with an equivalent single force, not two force components, but a single force and a moment, right? So let's work out the single resultant force. So we had a horizontal component, I think it was 169.3. We had a vertical component of 90.4. All right, and so if we just draw on the resultant, all right, so let's call that F sub res. Let's define that angle as alpha, and let's just calculate these. So we'll say F res is Pythagoras, again to the rescue, 169.3 squared plus 90.4 squared, square root of all that is going to be 191.9 newtons, okay? And alpha is going to be the tan inverse of 90.4 over 169.3, which should be 28.1 degrees. All right, so at this point we have all of the bits and pieces we need. We've all of the information we need to draw this equivalent force system. And it's a very simple force system to draw, right? Because it only has one force and one moment. So what we're saying here is that the moral of the story here is that we can replace the original system with the following. So I'm going to draw a set of axes first. So we said we had 100, let's draw it on in green here. We said we had 191.9 at an angle of 28.1. So just roughly sketching it. That's going to be 191.9 newtons, and the angle is 28.1 degrees, okay? And we also need to add on the clockwise moment of 68.6. So let's draw that like so. So that's your 68.6 Newton meters. And we're going to call this guy equivalent system B. All right, and so all we're saying is that we can look at system A here, and we can take all of those forces and moments, get rid of them all, and we could replace them, and it would have the exact same effect as the original system. And so we just replace all those forces and moments with a single force applied at the origin and a moment of 68.6. Okay, so that pretty much wraps up all we want to say about forces, the moments of a force, and equivalent systems. So hopefully you found that helpful. We'll leave it there for now and pick it up in the next one.